Okay, in this video, we're going to talk about the conformational analysis, or talk about conformational analysis, and we're going to do an example on butane, okay? So conformational analysis is just basically looking at molecules through Newman projections and then rotating a specific bond, okay? So let me just number our carbons here. So here we have the molecule butane. I'm going to number my carbons 1, 2, 3, and 4. And what we're going to do in this exercise is really rotate this bond between carbon 2 and carbon 3. And by rotating that, we're going to understand the energetics of the molecule when it's in a different conformation. So when we rotate bonds, right, we're getting a different conformation. Right, so I can draw butane another way. I could draw butane like this, right? That's still butane. Okay, and when we do that, we see that these are different conformations of the same molecule. They're both butane, but they have different conformations because I have really rotated this center bond. All right, so let's take a look at how we do this. So we're going to draw a Newman projection. What we're going to do is just look down the bond between carbon 2 and carbon 3. So let's draw our Newman projection. We draw a circle. I see carbon 1 is above my eye in the plane of the board. So there's going to be carbon 1. There's 2 hydrogens coming off to the side. I look in the back, carbon 3, right? Carbon 4 is pointing down below my eye. So there's carbon 4, and then again we have 2 hydrogens that are up and to the left and upper to the right. So if I draw my carbons, there's carbon 1, there's carbon 2, carbon 3 is blocked by carbon 2, and there's carbon 4. And in our example here, I think they have carbon 4 in red, so I'm just going to write here Me, right? So remember, like I can leave this 1, I can leave just a line there that means I have a methyl, right? I could write Me, same thing. I could write CH3 for carbon 1, all means the same thing. So I'm just going to leave that kind of as a blank line, right, knowing that we have a, knowing that we still have a methyl there. So let's get rid of that. Great. Okay, so here's the first Newman projection that we're going to start with, and what you'll see is that is this Newman projection down here. And what we can see is these 2 methyl groups, right, carbon 1 and carbon 4 are opposite each other. And we can see that here. Okay, so what we're going to do in a conformational analysis is I'm simply going to rotate either the back groups or the front groups 60 degrees at a time and then draw a new Newman projection. So here's our first example. If I rotate this clockwise, the methyl is now going to go behind the H. The H will go behind the methyl, and that H will go there. And that gets me my second Newman projection. You can see it's kind of hard to draw these. I can't draw them directly behind it because then I can't see it. So I kind of draw a line so they're really, really close to each other. Okay, so that's our second. Next, we'd rotate the methyl to that open space, H to that open space, and that H there. This gets us our next possible Newman structure. Again, we're just rotating the bond between carbon 2 and 3. And then we continue to do this. Rotate the methyl behind that methyl, the H behind that H, and the H over there. That gets us our next Newman projection. I can rotate the methyl again 60 degrees, and both H's 60 degrees. That gets us our next Newman projection. Again, I can rotate these again. Now this methyl's behind the H, this H is behind that H, and that H is behind that methyl. And then I can do one more rotation here, where I now get back to exactly where I started. So really what we see is we have 1, 2, 3, 4, 5, 6 different conformations for butane. okay? So what we want to do now is kind of talk about and think about sort of the consequences of how these are rotated and the energy associated with it, all right? So what we should notice here is we're now plotting the energy levels of these, right? We're plotting the energy levels of these at different levels. So there's 1 level, 2, 3, 4, 5, 6, and then back where we started, all right? So the first thing we should see is when we have the 2 methyl groups anti, right, when those 2 methyl groups are anti, that really gives us our lowest energy here, and that's at the end. If we look, as I increase anti up over here, right, that's high in energy, back low in energy, high in energy, low in energy, high in energy, low in energy. So we see that every other structure, right, is lower in energy. Okay, now they're not equal in energy, but they're lower in energy. These are our staggered forms. So what we're going to see is our staggered Newman projections, right, where there's lots of space in between, are more stable than eclipsed. So these structures in red, where the methyls and the hydrogens are directly behind each other, those are higher in energy. Okay, so those are eclipsed conformations when the groups are directly behind each other. So staggered is always more stable than eclipsed. So here are our eclipsed functions, here, here, and here. So the first thing we see from this diagram is staggered is more stable than eclipsed. All right, so let's clear this out. So we can kind of work and visualize this again. Okay, so I'm going to highlight eclipsed, 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 here, here, and here. Those are higher in energy than the staggered conformations, right? Staggered, 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 staggered. All right, there's our staggered energy conformations here. So staggered is more stable than eclipsed. So that's the first thing we see. But we should notice is that not all staggered is the same. These structures here are called Gauss structures. They are not as stable as the anti-structure. So anti and Gauss are all staggered, but these Gauss interactions are not as stable. All right? So what does that mean? Right? Let's understand what the word Gauss means. So the most stable molecule is when these 2 methyl groups are opposite each other. And what that means is they're not bumping into each other at all. There's no extra energy of having those close to each other. So we have to remember when we have atoms, those are surrounded by electron clouds, and those electron clouds are negative. So if they get too close to each other, that causes a repulsion and makes the molecule higher. Okay, so that's why eclipsed is really bad, is high in energy, because these methyls and hydrogen groups are right behind each other. They're bumping into each other. So that means these are really, really high in energy. These 2 methyls are bumping into each other, right? Here we have a methyl and a hydrogen, 2 hydrogens bumping into each other. That causes the molecule to be less stable. It's high in energy. But focusing in on sort of our Gauss interactions, okay, let's go back to what that means, and let's see what a Gauss interaction is. So in a Gauss interaction, what we see is we have these 2 methyl groups here, and they are close to each other, and it turns out that destabilizes the molecule by 3.8 kilojoules per mole. So this is called a Gauss conformer because these two methyl groups are bumping into each other. One methyl group is in the front, the other is in the back. In this example here, again, we have a Gauss interaction. Those two methyls are bumping into each other. The methyl in the front and the methyl in the back are bumping into each other. They're too close, which makes this staggered conformation less stable than the anti-conformation. All right, the most stable conformation is when we have our two methyl groups as far away from each other as possible. When you have a Gauss interaction, these two groups, these are anything that's not a hydrogen, are going to bump into each other, right? So we don't call two hydrogens Gauss, right? Because we have to have an atom there, right? So hydrogen is going to have the least amount it's not going to cause any energy. So anytime we have any two groups, it could be two methyls, it could be two ethyls, it could be methyl and a chlorine. That's a Gauss interaction, and it raises the energy of the molecule a little bit. Two methyls specifically raises it by 3.8 kilojoules per mole. All right. Staggered is always better than eclipsed, right? But if we can, we want to have our largest groups opposite because that doesn't have a Gauss interaction, which raises the energy of the molecule. Okay, so a Gauss interaction is when you have two groups, two of any groups, one in front, one in back, next to each other. One thing to think about this Gauss interaction, two methyls cost you an energy of 3.8 kilojoules. What if these were ethyls? What would that do to your energy? Well, ethyls are larger than methyls, so that would raise this up even higher. It would be greater than 3.8 kilojoules per mole as compared to the anti-version. All right? So let's kind of look at like how we got these numbers. Where do we get 19 and 16 and 3.8? Where did all these numbers come from? Okay, so it turns out we have a really good feel for what these numbers are because we can kind of estimate what the cost is from different conformations. Okay, so the first thing we'll talk about is a methyl-methyl Gauss interaction. It turns out that costs you 3.8 kilojoules per mole or 0.9 kcals per mole. So in this graph, we're looking at kilojoules per mole. So you can see this energy difference here from that Gauss interaction is 3.8 kilojoules per mole because these two methyls are bumping into each other. So that's why the anti is more stable than the Gauss by 3.8 kilojoules per mole. And these numbers here you don't have to memorize. Obviously, all of our assessments will be open notes, but you don't need to memorize. If you ever need to use these numbers, I'll give them to you. But let's look at sort of the eclipsed, right? Let's take a look at the eclipsed energies. Let's see if we can calculate why this particular Newman projection is 16 kilojoules per mole and why this particular one is 19 kilojoules per mole. So if we look at sort of our first example here, number 1, you can see that we have 3 bonds that are eclipsed. We have a methyl hydrogen that's eclipsed. We have another hydrogen methyl that's eclipsed, and then a hydrogen that's eclipsed. So we can use this table to calculate that. Here we have 1 hydrogen eclipsed, right? That's 4 kilojoules per mole. And then we have 2 hydrogen methyl eclipsed plus 2 times 6, right? So that's 4 plus 12. That equals 16 kilojoules per mole. Okay, so this conformation is 16 kilojoules per mole higher than the anti-form. All right, and we can just use this table to calculate those numbers. What about this conformation here? Let's look at this one in blue. Okay, we're going to see that comes out to, this is 19 kilojoules higher than our anti-form. Why is that? Well, here we have two methyls that are eclipsed with each other, 2 hydrogens that are eclipsed, and another 2 hydrogens that are eclipsed. So here we have a methyl-methyl eclipsed. That costs you 11 kilojoules per mole. And then we have two hydrogen-hydrogen eclipsed. So that is 11 plus 2 times 4. That equals 11 plus 8. That equals 19 kilojoules per mole. All right, and that's the exact number we have here, 19 kilojoules per mole. Okay, so basically what we're doing is we're using Newman projections. We're rotating that bond, looking at all the possible Newman projections to understand the relative stability of different conformations. All right, and it turns out the most stable conformation we can have is when these methyl groups are opposite each other. Okay, so that's why when we draw molecules zigzag, right, we draw them in this zigzag conformation, because if I look through a specific bond, one group is up, the other group is on the opposite side, that gives me an anti-conformation looking through that bond. So why we draw molecules zigzag is that's generally the most stable form that we can have.